study is reflection and refraction. Instead of bending around behind the barrier, the wave might bounce off, and that's what reflection is. So for reflection, we're going to say that waves bounce off a barrier. Okay, so I'm going to draw a barrier here. Could be a mirror, table, whatever. And I'm going to have a wave approaching it this way. It's going to hit the surface, and when it hits that surface, it's going to bounce back off this way. I'm going to label this the incident ray. Incident means the ray of light or of the wave that's coming into the surface. I'm going to call this the reflected ray. Now, it's just like a pool ball, okay? If I'm playing pool and I send the ball into the bumpers at this angle, it's going to come back out. These two angles are going to be equal. But they don't measure those angles. For some reason, okay, way back when people started talking about reflection, they decided to measure all of their angles from a normal line. Remember, normal means perpendicular. The normal force from this table is going to be upward perpendicular to the table. The normal line is perpendicular to the surface. And we always measure our angles relative to that. So this is going to be theta I for the incident angle. This is going to be theta R for the reflected angle. And the law of reflection says that theta I is going to equal theta R. So it's pretty simple. The only way they could trick you was something like this, and you don't have to draw this, but if they give you this problem, and they say this is 60 degrees, and they'll say, what is the angle of reflection? You're going to be tempted to put 60 degrees. But you have to remember that there's a normal line here. The incident angle is actually 30, so the reflected angle would be 30. Next thing we're going to talk about is refraction. And refraction is when a wave bends when changing materials. The reason that it occurs is because the wave changes speed. So I'm going to draw an example of this. We're going to have our boundary right there. Okay, we're going to have one material up here, another material down here. For right now, we'll just call this material 1. And we'll say that whatever the wave is, it travels fast in that material. Most of the time, these are going to be light waves, and this might be a vacuum, because light travels the fastest in the vacuum. The speed of light in a vacuum is 3 times 10 to the 8th. This might be another material, material 2, where the wave travels slower, so maybe water or glass for light. We always say the speed of light is 3 times 10 to the 8th, but that's in a vacuum. It can be slower, or it will be slower in any other material. Now, I'm going to draw, my light's going to come in, say, at this angle, or my wave is going to come in at this angle. Okay, and then we're going to figure out which way it's going to bend when it gets into this second material. I'm going to do that by drawing in the wave crests. So my wave crests are going to be parallel lines that are perpendicular to the way the wave is moving. So like so. And you want to try to draw them nice and straight and the same distance apart as much as you can. So here's my waves coming into this barrier. And you can think of them as waves coming, like into a beach or something like that. Now, what's going to happen when they get to this barrier? Well, if, and don't draw this line at this moment, if the wave didn't change speed, the wave front would stay nice and straight like this, okay, and these would just continue going this way. But because it's slowing down, when it gets to this material, it's going to lag behind. So instead of doing this and staying up with it, it's going to end up getting behind it. So it's going to look like this. Oops. it's going to end up lagging behind it a little bit, so like this. So draw these lagging behind. They're going to be parallel to each other as well. And they're going to look something like this. And I'll keep drawing these in. Oops, that last one was a little too close. But anyway, they're going to end up lagging behind, and now you can see they're not going this way anymore, now they're going this way. So the wave is now traveling in that direction, perpendicular to those lines. Now, we mentioned before that these are crests, so the wavelength is the distance between the crests. So I'm going to label this wavelength 1 for material 1, and it's the same over here, is the distance between these. And wavelength 2 on the other side is going to be between any two crests, and the wavelength got smaller. Okay, so we're going to make some notes here, okay, that when you go from fast to slow, okay, this fast material is slow material, the velocity decreased, okay, by definition it's going slower over here. Now the wavelength decreased, okay, we want to make a note of that. These wavelengths over here are shorter than these wavelengths. And we want to talk about our angle. Now again, we have to draw in a normal line because our angles are always relative to our normal line. So I'm going to draw in my normal line right where this ray is hitting it. This would be theta 1 for the incoming angle right here. This is theta 2. And the angle got a little bit smaller. Here it was a little bit bigger, here it's a little smaller. So we can say that the angle also decreased. So we'll make a little note in something fast. Okay, V is larger, lambda is larger, the angle is larger, but there's one thing to keep in mind, and this is going to be kind of important, the frequency is constant. So I'm going to make a big box around that. The frequency stays the same. So I'm going to do another little example. You can maybe draw it on another piece of paper, or you could maybe put it over the side or just follow along and pay attention. But if I'm going to give an example like this, I'm going to say the barrier is this way now. My wave is coming in like this, and then bending like that. And I want to know which material is faster, where the wavelength is longer, and so on. Well, before you do anything, make sure you draw in the normal line. So I'm going to draw in my normal line perpendicular to the surface right here. This is material 1, so I'll call this theta 1. I'll call this theta 2. All right? Now, where is it faster? Well, it's faster where the angle is larger. So now I know that this over here is the fast material, and this over here is the slow material, because the angle is bigger on this side than it is on that side. Okay, the other thing is the wavelength. The wavelength is going to be bigger on the fast side, the wavelength is going to be smaller on this side, and the frequency on both sides are going to be the same. Now, a little bit later on, we're going to start doing some math with this, but for right now, if you can pick out which is the fast side, which is the slow side, which way the wave is going to bend, you are in pretty good shape.